Right, so in this video I'm going to run through CC11, which is extracting and using metals. It's also the chapter that contains the reactivity series, which is what we're going to start with. Top of the reactivity series, you've got your group 1 metals. They only have 1 electron to lose, and it's easier to lose 1 electron than to lose 2 or to lose 3. Of your group 1 metals, potassium's the most reactive. Okay, the bigger they are, the easier they find it to lose an electron. So potassium's first, then sodium, then lithium. After group 1, you're going to have group 2, calcium and magnesium. And again, it follows the same trend. Calcium is bigger than magnesium. Because it is bigger, it finds it easier to lose its outer electrons. After group 2, you're going to have group 3. So aluminium is in group 3. So this top of the series is all quite logical. The rest of it you do just have to learn though. So after aluminium, you can see here I've got carbon. Carbon's not a metal at all, but we need to know its place so that we can use it for extracting metals. After carbon, you've got zinc and iron, 2 transition metals. You do just need to learn the order. Hydrogen, again, not a metal, but we need to know its place so that we can predict the products of electrolysis. And then at the very end, you've got copper, silver, and gold. Again, transition metals, all very unreactive. If you wanted to kind of investigate which metals were the most reactive, you'll need to react them with something. So if you were doing the very top of the series of potassium, sodium, lithium, calcium, because these guys are all quite reactive, you would just react them with water. You wouldn't throw them into an acid or anything like that. You would just use water. And these guys will all just react with cold water. You don't even need to increase the temperature. And when you're reacting these guys with water, you're always going to produce hydrogen. Hydrogen is a gas, so you're going to see fizzing. And you can just use your observations to see which is the most reactive. So if you remember with potassium, it will move really quickly across the surface of the water. You'll get very vigorous fizzing. Something like calcium won't fizz as much, and that will tell you that it's less reactive than potassium. If you wanted to do magnesium, aluminium, zinc or iron, so this doesn't apply to carbon, but magnesium, aluminium, zinc or iron, they won't react with cold water, which in itself is telling you they're not reactive. But if you raise the temperature and react them with steam, they will react. And again, if you react them with steam, you do produce hydrogen gas, so you can use the amount of fizzing as a measure of reactivity. You could, I was supposed to say or, not and, you do one or the other. You could react them with an acid, okay? Metals and acids form salt and hydrogen. Again, these guys all form hydrogen. You can use the amount of fizzing as a measure of their reactivity. Copper, silver, gold, they don't react. Whether you're adding them to steam or to an acid, you're not going to see anything. The other thing that you can do to kind of more, kind of quantify the rate a little bit more is you can measure temperature. They're all exothermic reactions. When you react a metal with water or steam or an acid, it'll be exothermic. So you can get the temperature of the water at the start and the temperature at the end. And whichever metal gives you the greatest rise in temperature, whichever reaction is the most exothermic, that metal is the most reactive. So it's just another way to quantify the rate of reactivity. Right, press pause. Do questions 1 and 2 on page 29. Please just pause instead of copying. See if you can actually write out the reactivity series for yourself. So I've got the answers here. First one, just the reactivity series. Again, I've just highlighted carbon and hydrogen, non-metals but included. An investigation. All right, so you're going to add, because I'm asking you magnesium, aluminium and copper. I originally wrote water, but acid is better here. They won't react with cold water. It would have to be steam. So you're adding them all to an acid individually. So you do them one at a time, and then you're going to record your observations. To make it fair, you'd use the same mass of the metal, the same volume of acid each time. And then what are your results? So they're always going to produce hydrogen gas. The metal that produces the most fizzing, the most vigorous fizzing, that's the most reactive. Copper won't give you any fizzing, so you'd say that was the least reactive. Your other option would be to use a thermometer, get the temperature of the acid at the start, temperature at the end. They are exothermic reactions, and the one that gives you the greatest temperature rise is the most reactive of the metals. That's just a simple experiment. If you were asked about potassium, sodium and lithium, you'd do the same thing, but you would use water with the most reactive ones. You wouldn't add them into an acid. Okay, so the other thing the reactivity series is used for is to predict methods of extraction of metals. And by that, iron, okay, something that you can use to build things. It's used in construction, you can use it to build a bridge. You're not going to find iron, pure uncombined iron, out in the environment. It's reactive enough to react with oxygen, and when it does, it forms iron oxide. Now, iron oxide is rust, so it's kind of a brown flaky powder. You're not going to build a bridge out of that brown flaky powder. So you need to get the iron back from the iron oxide. And the way you'll do that is through a displacement reaction. So anything that's more reactive than iron can be used to take iron's place next to oxygen, leaving iron by itself as a pure element that you can go and build stuff with. Now there's lots of options here, lots of things that will work, but potassium and sodium themselves, I mean, they're rare, they're also reactive, they're hard to handle, they're expensive. So you're not going to use these reactive metals, even though theoretically the chemistry is fine, it's just not practical. Carbon, on the other hand, and this is why we have it in the series, carbon is just coal, so it's unreactive and easy to store, and we've got it readily available. And if you take your iron oxide, which is essentially a big bag of rust, and you heat it up in the blast furnace, and you do need incredibly high temperatures to drive this reaction forward, but if you heat this in the blast furnace, because carbon is above iron on the reactivity series, carbon will take iron's place, and what you're going to get is carbon bonded to oxygen, so you're going to release carbon dioxide. Now if you wrote carbon oxide, they typically give you the mark, but it's carbon dioxide, and then you're left with iron now all by itself, so it doesn't have the oxygen anymore, and it will literally go from looking like this big bag of rust, this brown flaky powder, to being proper like iron metal that you can use to build stuff with. So I'm using carbon to extract iron from iron oxide, and I can do exactly the same with zinc. If it was zinc oxide, I can extract using carbon. I could do the same thing with copper. I could extract copper from copper oxide. I could extract it from any type of compound. It's just typically oxides because that's what they react with in the environment. At the very bottom here, something like silver and gold. Gold is so unreactive that you can find it pure in the environment. You don't need to extract it, but all the others, copper, iron, zinc, they're going to react with oxygen, and you need some method for extracting it. Now this particular method is called reduction with carbon. And the reason it's called reduction with carbon is one of our definitions for reduction is just that you're losing oxygen. And you can see here that the iron oxide loses oxygen and becomes iron. So I can say the iron oxide is reduced, and it's been reduced by carbon. If iron oxide is getting reduced, something else has to be oxidized, and it's carbon that picks up oxygen and will be oxidized. Now, anything above carbon on the reactivity series, this reaction is not going to work. If you have aluminium oxide, and aluminium is another very useful one. You use it to make aircrafts. It's like a light metal. If you have aluminium oxide and carbon, because aluminium is more reactive, this reaction doesn't work. They don't swap places. Doesn't matter how much you heat it, you're never going to get pure aluminium. So, I mean, again, you could pick something else from up here that is reactive enough to displace aluminium, but these guys are expensive in themselves. You don't have lots of spare lithium floating around to be able to do this en masse. So everything above carbon in the reactivity series, if you want to extract it from a compound, you are going to be using electrolysis. All right, so the method that we looked at last week, you're going to use electrolysis. So if you had sodium oxide, you'd use electrolysis to separate the sodium from the oxygen. You're not going to use a metal more reactive. Downside of electrolysis, incredibly expensive. All right, these are ionic compounds. You have to melt them. We saw last week that if you dissolve them in water, you're going to form hydrogen at the cathode. You're not going to form the metal. So if you've got aluminium oxide, you have to heat it to incredibly high temperatures. It has to be molten aluminium oxide, and then you'll electrolyze it in order to get pure aluminium. So very, very expensive, and this method is preferred just to avoid using electrolysis. Not without drawbacks though. You are producing carbon dioxide, which we know is a greenhouse gas, and as I said, you do need very high temperatures in the blast furnace. All right, have a go at 3, 4, 5, 6 and 7 on page 29. So answers, anything above carbon is extracted using electrolysis. I picked aluminium. Zinc, iron, copper, all extracted using carbon. Do not need to be extracted. That would be gold, something at the very bottom. Oxidation is the gain of oxygen or addition of oxygen. Reduction is the loss or the removal of oxygen. Complete the following reaction. Carbon can displace iron, so you get iron by itself and then carbon dioxide. What is oxidized? It's the carbon that's oxidized. It's the iron oxide that is reduced. Make sure you don't say that the iron is reduced. Reduced means it can lose oxygen. Iron doesn't have any oxygen to lose. Iron oxide has oxygen to lose. So iron oxide is reduced to form iron. Just as a hint, anytime you're ever asked what's oxidized or reduced, you have to pick a reactant. Your answer will never be a product. It will always be a reactant. Why can aluminium not be extracted? The language I've used here is straight from the mark scheme. So carbon is less reactive than aluminium, so carbon cannot displace aluminium. So less reactive, so carbon cannot displace it. What would you use then? Instead, you're going to use electrolysis. Problem, you're going to have to use molten aluminium oxide. You need really high temperatures to keep aluminium oxide as a liquid. To generate those temperatures, you're going to have to burn a lot of fossil fuels, and A, that's expensive, and B, that will also release some CO2 into the environment. So don't just say high temperatures, explain, and again, try and give more. Don't just say expensive, say why it's so expensive, because the fossil fuels you'll need to burn, which is expensive to generate those types of temperatures. All right, the next thing we're just going to look at is just other displacement reactions. So you can use displacement reactions to confirm order of reactivity, another method. And we also need to be able to show that these are redox reactions. So I've got zinc and I've got copper sulfate. Zinc is more reactive than copper, so zinc will take copper's place. That means zinc will pair up with the sulfate, so I'll get zinc sulfate, and I will get copper. So we use displacement reactions in CC13 to prove that the halogens got less reactive going down the group. And we said in those cases you always had to say what the colour change was so that you knew that the reaction was taking place. Similarly here, if this reaction's taking place and zinc really is more reactive than copper, you will see something. You can't say bubbles. There's no gas being produced here. You're starting off with zinc as a metal, which is a solid. You've got copper sulfate, which is in solution, aqueous, and then you're going to form zinc sulfate, which is in solution, and you're going to form copper, which is a solid. And you have to say what you would see. Now, the only salt you're expected to know the colour of is copper sulfate, and it's blue. Okay, we saw that in electrolysis last week. Okay, it's a blue salt. So what's going to happen is that blue colour is going to fade. All right, your blue colour will fade because, again, as we learned last week, it's the Cu2+ ions responsible for the blue colour, and those copper ions are being converted back to copper. So that blue colour of the copper sulfate is going to fade. The other thing you could say you will see is you're forming copper. Well, what does copper look like? You're going to see bits of brown metal forming. Okay, zinc is a silvery metal, so you'll see the zinc disappear, the silver metal disappear. You'll form the brown metal instead, and as I said, that blue color will fade. So because you're seeing those observations, you know the reaction is taking place, and that confirms that zinc is more reactive than copper. So again, we can use displacement reactions to prove the order of reactivity. Other thing you're going to be asked to do is redox, to write half equations to show what's being oxidized and what's being reduced. So if I just write this as a symbol equation, zinc plus copper sulfate goes to zinc sulfate plus copper. When zinc is an element, okay, it's got no charge at all. When it's part of this compound, it's got a +2 charge. And I know it must be +2 because sulfate is -2, and I only needed one zinc to balance out the 2 negative charge. Copper here, again, it's got a +2 charge for the same reason, and as an element it's just going to be 0, so no charge at all. So using this I can then write myself some half equations. So zinc starts off with no charge at all but ends up with a +2 charge. So what's happening to zinc to make it end up with a +2 charge? Well, it must be losing 2 electrons, and if it's losing electrons, I can say zinc has been oxidized. What's happening to copper? Well, copper starts off with a +2 charge. It ends up with no charge at all. So it had lost 2 electrons. It must have gotten them back to end up as neutral copper. If it's gaining electrons, it has been reduced. again, press pause, have a go at 8 and 9. So answers for 8. Oxidation and reduction. Oxidation is loss of electrons, reduction is gain of electrons. So you're just using oil rig. Just make sure you do specify you're talking about electrons. Your displacement reaction. Magnesium's more reactive than copper, so takes its place, showing that it's redox. Magnesium starts off as an element, so it has no charge. It ends up in an ionic compound with a 2+ charge. It must have lost 2 electrons, therefore it's oxidized. Copper starts in an ionic compound with a 2+ charge. It ends up as an element with no charge at all. It got back its 2 electrons, therefore it is reduced. Again, anytime you're asked to explain redox, please just give half equations, and they pick up all of your marks without you having to describe what's going on in words. Alright, so the last little bit about the biological methods of extraction. So what I've attempted to draw here is phytoextraction. It's basically when you plant some trees on soil that contains low-grade ores. So ores are rocks that have metal ions in them. And what will happen is, because you've got metal ions, say for example you've got copper ions in the soil, because copper ions are aqueous, so they're dissolved in water, the ions can be absorbed by the roots of the plant. Alright, so really important to notice the fact that they're ions and they're aqueous. If it's a big lump of solid copper, that cannot be absorbed by the roots. But the plant will absorb lots of ions into their roots, and then they harvest the plants. So they pull them up, they burn them, and from the ashes they're able to harvest bits of metal. So it's called phytoextraction. Advantage: you can extract metals from contaminated soil. Also, it means you don't have to go mining for new ores. If you know that there are ores there and you're able to get the copper from them, that's better than going mining. Mining is, ruins the landscape. It's also dangerous. Disadvantages: this is still expensive. It's slow because you have to grow trees, and it's expensive because it requires people to plant the trees and then cut down the trees and then harvest the trees. So it's not cheap. The other disadvantage is that it's weather dependent. You have to be able to grow the plants, which can be weather dependent. Your other biological method, what I'm trying to depict here, is bioleaching. In bioleaching, you take bacteria, some little green spots there, that's bacteria, and the bacteria are able to break down certain ores, and when the bacteria break down the ore, they release metal ions into solution. Now, again, end goal here is not metal ions, okay? So if you were to get Cu2+ ions, that's not good to you. You want copper. You want it as a metal. So you have to reduce those ions back to copper metal. But usually what they use is just a displacement reaction. They'll use solid iron, just scrap iron that they've got no other use for. The iron will be oxidized, so you'd have your iron as solid scrap iron, losing 2 electrons and becoming Fe2+. So the iron will be oxidized and will supply the electrons for the Cu2+ ion to be reduced. So that is bioleaching. Advantage, advantage is you can make use of these low-grade ores, and you don't have to go mining. So mining, always mention mining as a disadvantage. Destroys landscape, it can be dangerous, but a disadvantage of bioleaching, again, it's slow, and you produce some toxic waste products. So sulfuric acid is produced in this process, and that's toxic to the environment. So that will be your disadvantage of bioleaching. Right, do questions 10 and 11, and then we'll do LCA. Alright, we'll just go through the last few questions. So phytoextraction, you're going to grow plants in soil that contains low-grade ores. Metal ions, you have to specify that they're ions. Chunks of solid metal can't be absorbed, but metal ions can be absorbed into the roots. So the metal ions concentrate in the roots of the plant, and then you can burn them and extract the metal from the ash. An advantage, it reduces the need to mine, and mining is bad for the landscape. A disadvantage is it's slow and it's weather dependent. Bioleaching, bacteria break down low-grade ores into a solution. The solution is called a leachate. And it contains metal ions. Again, you need to turn those metal ions back into metal atoms, so you're going to have to reduce the metal ions, and you'll do that using scrap metal, usually scrap iron. Advantage of bioleaching, again, conserves ores and reduces the need to mine. Mining is bad for the landscape. And a disadvantage, it produces some toxic material, most notably sulfuric acid. It's also slow. Advantage and disadvantage, I'm just going to go through recycling. Advantage of recycling, again, conserves ores, reduces the need to mine, and you're putting less waste into landfills. That's all positives of recycling. Negatives, it is expensive. You have to collect, you have to transport, you have to sort, and sometimes with the kind of transporting, your kind of CO2 output is quite high, so it's not quite as environmentally friendly as you might think. But yeah, also it is expensive, but you can't just say expensive, you need to say why it's expensive. An LCA, life cycle assessment. Basically, if you want to manufacture a new product, you need to consider a few things. You need to consider what are the raw materials, where are you going to get them, is it a renewable or non-renewable resource that you're using, energy needed to manufacture them, where are you going to get this energy from? Again, are you going to be burning fossil fuels as part of manufacturing your product? What's the product actually going to be used for? And then again at the bottom, how will you dispose of your product? They're all things that you need to consider. That was CC11 in an absolute nutshell. Obviously do the exam questions. It's not really a chapter for lots of recall. It's more kind of application based questions, which you'll see in the exam questions. So just make sure you're paying attention to the mark schemes there, and then adding things that you maybe didn't get from this video to your notes so that you are well prepared.